Okay, dear student, let us see what is there in this question. Three identical secondary coil PQR are wound onto the iron core of a transformer. The coils form a power supply that provides two output voltages, one between A and B, and another between C and D. The primary coil of the transformer is connected to 110 volt RMS mains supply that is written in the diagram. Okay, primary coil has the number 1500 turns. Okay, each secondary coil is having 75 turns, so these are all 75 turns. Okay, no problem. Let's see, 110, that is written 1500. Two of the secondary coils P and Q are connected in series to a diode bridge. There is no load resistance between A and B. X and Y are the points in the circuit connected to the ends of the coil. Calculate the peak EMF between X and Y. RMS is given. We are supposed to find the peak value. Okay. Okay, let's see. Yeah, so see, the RMS value, input value is given as 110. Be very careful, the RMS value is given, but they're asking you the peak value. So we will see. So this is the RMS value, which is kind of an average value. So we will work around with average. Later we will find the peak. So the number of turns given here is 1500 and number of turns here is 75 and here also 75. So I can clearly say that N2 is equal to 150. 75 plus 75. So both of these coils, they are in series. They are shown separately, but that doesn't make any difference because they're connected with the same wire. So how does that differentiate? It does not differentiate. So N2 is 150, this is 1500. Clear. And we have to find the voltage across X and Y. I think this was the question. Find the peak voltage between the X and Y. Okay. So we would be using the formula E2 divided by E1, N2 divided by N1. This is known as transformation ratio. Transformation ratio. This is E2 divided by E1, N2 divided by N1. So E2 we want to find, and E1 is given as 110, N2 is 150, and this is 1500. Clearly this is 10. So E2 is coming out to be 11 volt, but this will be the RMS value. It will not be peak value. Why RMS? Because we are using 110 volt, which is RMS. So we know the formula. So VRMS is equal to peak value divided by square root of 2. That is the value we are going to use. From here we can find the peak value. That will be like in the case of E, like don't be confused. Sometime I'm using V, sometime I'm using E. So don't be confused with that. So I can clearly say E2 peak voltage will be equal to the RMS value. Sorry, peak voltage here. V naught is equal to root 2 multiplied by the RMS. So the RMS value that we got is 11. So your answer will be 11 root 2 volt. That will be the peak voltage. Peak voltage at X and Y. So the answer will be 11 root 2. This is how we do it. Let us see what is given in the mark scheme. They are saying 16 and I like, yeah, 11 root 2. Yes, I'm getting 15.5 to be exact. But again, we just want to have two significant figures. So we will report it as 16 volt. That's it. So this is done. Now let us go to the next question. The graph between shows the variation with time of the output EMF between X and Y. So the graph shows the variation. X and Y. Okay. So X and Y is kind of input there. Let me show you what is happening. Try to understand this. See, this is X and Y. So X and Y is the input voltage for the star formation of the diode, isn't it? The diode rectification. So this is the input signal, which is X and Y, and it is already given there. The graph is simple, going like this. So that is simple alternating EMF. The only thing is, this is a transformer, this is primary, this is secondary coil. Because of the transformation ratio, the voltage is up and down, but the variation is still alternative. Some values are positive, some values are still negative. Rectification has not yet taken place, so this is a full wave rectification circuit. So in A and B you would be getting a full wave rectified voltage. So graph is, the question says, draw the graph of the voltage that we are going to get in A and B. So this is a full wave rectification model. There is another system which is half wave rectification. In paper one questions for the topic 11.3, you can go and verify for the paper one questions. I have completely given you explanation for, like, detailed explanation for full wave rectification and half wave rectification. So at this point, what will happen? You see, the positive value will remain positive. The negative value will be shifted into the positive domain like this. So this is what we are going to get there. So how our graph will be looking like? You see, this is the graph, and we want to make a graph between A and B. Draw on the graph the variation of the potential difference between A and B with respect to time. Let's see. So this positive graph will remain positive. Negative graph will be shifted to positive. Positive will remain positive. It will be like this. Simple. Let us, I will show you the mark scheme later. Let us not waste time. Let us go to the next question now. A resistor is now connected between A and B. Now a resistor is connected between A and B, that is after the rectification. State and explain the reason why peak potential difference across XY will be smaller than the EMF you calculated in A1. State and explain the reason why the peak potential difference across X and Y will be smaller than the EMF you calculated in A1. Okay, let's see. Okay, so we can say here, like, if we have to answer it, because it is given in the question itself, that why the voltage difference will not be that big, like why it will not be equal to the peak voltage, it will be lesser. Clearly there will be some losses there, so we have to incorporate some losses. So now you see, I don't think that losses should be the correct answer, because loss will be taking place only in AB, provided there is a resistance in AB and there is no resistance otherwise in the circuit. So why there will be loss there? There will be no loss. But we can say that yes, the voltage induced here will be lesser than the peak voltage that we calculated. Why is that? Because according to the Lenz's law, like, see, this is the only explanation that I can think of, but this is actually not in your syllabus. There is a concept, and that concept is called self inductance. So according to that concept, we can give the explanation here. So what is that? When the current starts flowing, now because of the current, Lenz says that flux will be induced, isn't it? And when the flux of the coil will change, so there will be another induced current that will try to stop the that thing. So overall the voltage will reduce because there is a backfire. There is kind of backfire voltage, you can say. There's back EMF. Yes, the word is back EMF. So this coil itself will be producing an EMF which is called back EMF, and because of that, the voltage, peak voltage that this resistance will be able to will enjoy will be lesser than the peak voltage that we have calculated. I think that should be the only reason here. I can't think of any other reason. Let us see the mark scheme, what they want to say. We have to see it. Okay, here is the explanation. There is now current in the secondary coil. Yes, absolutely correct. Energy loss due to heating in the coils. Uh, Clearly, I don't feel that this is the correct reason. First of all, the coil, like the resistance of the coil, is not given in the question. So how can we clearly say that there will be losses in coil? Number one. Number two, um, um, like Okay, fine, no problem. Let's see. Lenz's law predicts that this will oppose the original induced EMF. Now, this is the correct explanation, I think, because Lenz's law will create a back EMF within the loop itself. You can call it self induction also. And because of that back EMF, this peak EMF will be facing an opposing EMF. That is going to reduce the peak EMF. That's it. So that will be the reasoning here, but it is highly ironic because we do not have this concept of self inductance in our syllabus. So I was really confused earlier because I thought that we should not be talking about it. But as we can clearly see, they have not used the word self inductance, but they have clearly explained it. Anyways, let's move to the next question and see what is there in the next question. Explain the potential. Yeah, this we have done. Let us go to C. Okay. Coil R is connected to a single diode and a load that consists of a capacitor and a resistor. The graph shows this thing. Okay, so now they're talking about the coil R. So I must show you the diagram first. Let us go back quickly and see what is happening to the coil R. So this is the primary coil which was having 1500 turns, and this is the another coil which is having 75 turns now, not 150. So the peak voltage, RMS voltage will be completely different, and there is this diode there. So this, there is only single diode. This is half wave rectification. This is half a wave rectification circuit. Now after this there is a resistance which is CD. So clearly CD would be having half wave rectification. So here the input will be like this, the output will be only half and the other half will be zero. Okay, like this. The negative region is deleted, only positive is allowed to pass through it. Negative is deleted completely, so this output is zero. It is like that. Clear? That is why this is known as half wave rectification, because half of the wave is rectified, another half is just wasted. But now we are also using a capacitor along with it in parallel with this resistance. And now we know why do we use it, because the capacitor gives you the smoothing effect. Okay, so I hope that you know the theory of it. Let us now move to the question and see what is question exactly asking. Yes, the coil R is connected to a single diode and a load that consists of a capacitor and a resistor. The graph shows the variation with time of the potential difference across the coil R, which is having 75 number of turns. And so this graph is already given. Sketch on the graph the potential difference between C and D, which is around the resistor, the load resistance that we have drawn. So point number one, half wave rectification will take place. For the negative region, it will be zero. First of all, this will be the half wave rectification without capacitor. But now there is a capacitor and there is a smoothing effect. What is that now? Smoothing effect is actually at this peak value, once the peak is like this, once the peak is achieved, after that, the charging of the capacitor has taken place and the capacitor is at a higher voltage now. But because of this weakening effect, the input voltage is reducing, but the voltage of the capacitor is already high. So instead of this input voltage, capacitor is able to push the current through the resistor. It means that now discharging of the capacitor starts. And so we would be using the exponential behavior of the discharging of the capacitor that we have done in topic 11.3. So it will move like this, and then it will go like this, again sinusoidal variation, and then again exponential, again sinusoidal, and this will also be exponential. So this is kind of smoothing effect. Two things that you have to note here. Number one, People say, and even books are saying, that this variation from this point to this point is a straight line variation. That is what is written in the books. But actually, it is not straight line variation, it is exponential. But the problem is that this time is very, very small, like it's in microseconds. So the exponential behavior for a microsecond thing will be approximated as a straight line. That is why the book says that this is a straight line variation. But technically speaking, it is not a straight line, it is exponential. So this is exponential behavior, but you can assume it to be a straight line, no problem. And then this. Now, the second point that you have to note here is actually this black is not there anymore. So this is the only output that you are getting. Clearly, the average here is now much higher than what it was earlier. So this is giving you a better direct current. That is why it is known as smoothing effect in a half wave rectification. I hope I'm pretty straightforward, clear. This is how we do it. So this is the answer. Let us go to the mark scheme and see. Although there is nothing to see in the mark scheme, I know this will be the graph there. Let us move to the next question and then we will go to the mark scheme. State and explain the effect of adding another capacitor in parallel with the original capacitor. So clearly, if two capacitors are added in parallel, along with the resistor. So these two capacitors will be added together because we would be having the equivalent capacitor there. They are in parallel, so the equivalent will be 2C. They will be just added. So we can remove this capacitor and we can say that might be that the capacitor is bigger. Obviously, when the capacitor was not there, there was no smoothing effect. So you added some capacitor and the smoothing effect was there. Clearly, if you are adding more capacitor or the bigger capacitor is added, smoothing effect is going to become even more smooth, isn't it? And that you can find with the help of the time constant also from the variation. Like if I talk about the current, this is the variation in the discharging of the capacitor, negative T by RC, and the graph was exponential like this. So what will happen if I'm going to increase this, like RC is multiplied by 2, what is going to happen now? So let us see. If this is 2, what is the T half for this thing? Just a moment, lambda t is 0.63 ln2 divided by this. So that will be RC into ln2. This is the formula for the half-life in the case of discharging of the capacitor. Clearly, if we are multiplying this capacitor with 2, the half-life is doubled. It means that graph is going to become even more, the slope is going to reduce, isn't it? Because the time has increased. So slope is reducing. It means that smoothing effect is becoming even better. So this is how we create, first of all, the half wave or the full wave rectification we do. So alternative current is converted into DC, and then because of the capacitor, we just flatten it, and so it becomes approximately a perfect DC current. So this is how we do this question. Let us go to the mark scheme and see what is the answer given in C and D. Yes. So first of all, this is the graph that we have, but it will not be starting from this. This is wrong. This is wrong. It will be up to this only, like this. It should be like this. It will not be like this. But anyways, adding a capacitor in parallel will increase the capacitor and thereby increasing the RC value, which is the time constant. So the half life is also increased. Idea that it makes the waveform more smoother. So instead of going like this, it will go like this now. That is why it is becoming even more smooth. So this is the explanation for this question, dear students. Okay, so thanks for watching the video and thanks for joining the YouTube channel. Please share the video with all your friends. All the best.